Hello everyone, welcome back to another IB Chemistry SLHL video. Today we're going to be looking at structure 3.1.5, which is metallic and non-metallic properties show a continuum, including the trend from basic metal oxides through amphoteric to acidic non-metal oxides. So first let's just look at this little word over here, amphoteric. What does that mean? So, something that is amphoteric is a substance which can react both as an acid or as a base. So what this means, it can either work as a proton donor or a proton receptor in a reaction. So let's just take a moment to look at our period 3 oxides and look at their properties. We start at the left with our sodium, and then at the very end we've got sulfur. Now we can see that here we've got our basic oxides, we've got acidic oxides, and in the middle, aluminium oxide is amphoteric. And these properties have to do with the electronegativity across these elements. Because over here, with our magnesium and our sodium, the kind of bonds that we will get between these two will be ionic. Aluminium, this is an amphoteric metal because, as we said, it can function as a base or an acid in a reaction. And its bond is, although ionic, does present some covalent properties due to its specific electronegativity. And then from silicon onwards, that is when we get purely covalent bonds. And in terms of acid deposition and this link over here, ocean acidification caused by increasing CO2 levels. So, carbonic acid, which is just the fancy way of referring to CO2, or naturally occurring, is ever so slightly acidic. So when this reacts with water, it's a reversible reaction, we get H2CO3. Now this will then give you a hydrogen plus ion and a HCO3 minus ion. And this then, HCO3 minus, can also form another reversible reaction to create yet another H plus ion and CO3 minus, which you might know is from our compound ions carbonate. This right here, we can see, is going to be ever so slightly acidic. And rain, in terms of acidic rain on its own is already ever so slightly acidic, but when numbers reach below 9.6, that is when rain is truly thought to be acid rain. Now, another environmental example of these oxide reactions would be looking into nitrogen. Let's make ourselves some space so that we can better look into that. So, nitrogen. Diatomic, and when bonded with water, we get 2NO. And this process is what occurs in engines under high temperatures. This then, with oxygen from the atmosphere, as it's released in exhaust fumes, releases nitrous dioxide, which is an irritant, which means it's probably gonna make your throat inflame. Your body's not gonna like that. You inhaling that, it's not gonna be very healthy. And this is actually also laughing gas. This right here can then react with water in the atmosphere to then create acid rain. Finally, we need to look at prevention of acid deposition, because we all know by now, hopefully, that acid rain is not good for the environment due to its corrosive, not only corrosive effects, but how it can affect, for example, water environments by changing the pH of the habitats for the fish, for example, how it can be detrimental as they're not used to and not made to live in those overly acidic or overly basic conditions. So in terms of prevention of acid deposition, one example that you need to know would be like crushing or just the washing of coal. And this is done to remove sulfur, specifically almost about 90% of the sulfur in it. And another way would be to add calcium oxide to sulfur dioxide. So you get yourself this right here, which will not be acidic. Now, sulfur, why is sulfur bad? Let's look right into that. So, sulfur. When you burn sulfur, you're essentially just adding oxygen to it. That's what that looks like. Sulfur dioxide then reacts with water, H2SO4, water in the atmosphere, as this can be a gas, and this right here, that's sulfurous acid. If you have 2SO2 plus oxygen, you can also get an irreversible reaction, 2SO3, which also can give you your sulfurous acid. Now, obviously, as I went over before, acid rain, corrosive, changes the pH of aquatic environments, not good. And that is all that we need to know for this topic. So, hope you enjoyed and that be helpful for your studies.